Hello, welcome back to another video. Today we are going to be going through some dual puzzles, and I'll real quick get into what the construction for dual is, which is that any mines must be in a 1x2 or 2x1 block. Basically, it just means that every mine must be in an orthogonal region of size 2. So you can see, like here, for instance, every mine has another mine that kind of paired up with it. But you can see here, this mine is alone, and this group of mines is of size 3, so it's also not allowed. And you can kind of even see here, even if there's like two, individual 2x1 blocks that you can kind of make out here, they're orthogonally next to each other, so they really just form a larger 4 mine-sized block. And so that is not allowed. We'll go ahead and get into a puzzle for this real quick. So first of all, this is kind of a recurring theme through a lot of these more, just region-based mine variants, is that even if, in a case where there's a 1 and there's only one way for a mine to go out, you can kind of determine that there can't be a mine here. And the reason for that is kind of similar, where this mine needs to connect up to another mine, right, in order to be part of a dual, or a domino, really, is what I'm probably going to call them. If there's a mine here, then this overloads the 1. Same kind of idea here, so we just know there cannot be a mine there. And then we can use the kinds of logic we've talked about before to determine there are no mines up there, just by the 1 regions here. We can actually kind of see that there are admittedly limited amount of spaces that mines can really go around this 4. And let's just think about what happens if, for instance, we know that there's a mine down here. We then know none of these are mines, and by the idea of dominoes, we know there must be another mine there. We can get rid of that. And this tells us that there are exactly now 4 mines left and 4 spaces left, so we would then see that all of these are mines, but you can see we have created a region of size 4, which is not allowed. We can then just remove that real quick. Another interesting kind of thing to consider is we know this one down here can't be a mine, because if it were, then in order to finish up a domino, we know there must be a mine there. Neither of these can be mines, and we've run into the same kind of problem where we need to fill in all of these in order to finish up the 4 clue, but that breaks dual. So we can then mark that one as a non-mine as well. Okay. So I guess the next kind of thing we can consider is what happens if this isn't a mine. We run into the same problem. You can kind of see here, because this can't be a mine just because there isn't any other open squares for it to have another mine with, and then we have 4 open squares with 4 mines. So we know this must be a mine. We can also similarly show that this must be a mine, because if it weren't, then we have run into... Well, no, actually, we can't show that. If this one isn't, then there is still a possibility where there's a mine here, it extends either this direction or the other direction, and also these are mines. So we actually can't rule that out quite yet, which is interesting. Maybe something I will instead consider is if this one up here is a mine. And this is kind of a common-ish trick with it, where the idea is that at most one of these 3 can be mines. We can kind of see what would happen if 2 of them are mines by just going through a few examples. We know either that there are 3 possibilities for putting 2 mines here. 2 of them kind of fall into an issue where there are 3 mines just in a group like this or this, and if we instead put them around here, we can see there's nowhere for this mine to go without kind of running into a different mine and making a group of 3, so we then have an isolated mine. And what this is basically telling us is that there can only be 1 mine at most up here, but that tells us our remaining 2 mines must be down here, making this one a region of size 3. So we then know that this one isn't a mine. And the main reason that I notice that is just because this is a fairly common pattern in dual puzzles, so I kind of already knew that that might be coming up. Something else that we can kind of see here is that if this one is a mine, for instance, we can see that regardless of where it goes, it will it will put 2 mines around this 2 clue and ensure that none of these are mines, which breaks our 4. So we know this can't be a mine. You can also see that this runs into the same problem, where if there is a mine here, for instance, then we can still see that we'll be underloading our 4. So we know that's not a mine. And lastly, we can actually also, I believe, yes, we can also determine that this one up here can't be a mine. And the reason for that is because, first of all, we know it can't go down because then the 2 is finished and we've run into the same problems before. So we know it must go to this side, right? And what this basically tells us is that there must be one mine at most in this region here. However, we already know that there can't be no mines down here, so we'll just say that the one mine is in here. But then we run into an issue with the other 2 mines where we need to put them around here. We can actually just, in general, I think, say that this one must have exactly 2 mines in it, because if we had more, then this 2 clue would be overloaded, but if it has less, then we run into the same problem where we need a group of 3. So we can just get rid of all of these, actually. This is just standard logic. We can see that there must be a mine there. And then from here, we can kind of consider what happens if we put a mine here. We can see that it can't really connect up either direction to make a dual or a domino because it will then run into one of these mines and create a group of 3. So we can mark that. And then we also know this can't be a mine because this is a completed domino. Alright. Now we know there are 3 mines around this 4. We can see that there cannot be 3 mines here because doing so would kind of run into this problem again where there's a region of size 3. So we know there must be exactly 2 mines here. That tells us that 1 mine is here. To finish up this 4. And something else we can kind of notice is if we extend this mine upwards, then we know both of these ones are non-mines. Right, just because if they were mines, we would have a region that's too large. But if we extend this direction instead, we can see that, importantly, this square is still not a mine. And since those are the only 2 possibilities, we know that this square will never be a mine. This is a pretty common pattern, especially if you just have a mine in a corner specifically, is that you know the one diagonally away from the corner of it cannot ever be a mine. So there we are. Something else we can kind of consider is just case-wise what happens with this 4 in either scenario. We know if it goes up, then there cannot be a mine there, and that these 2 must be mines to finish up the 4. And if it goes to the side instead, we can kind of go through a similar process of marking mines and see that this one is always a mine down here. Additionally, in the red case, we can see that there cannot be a mine here. We also actually know that there can't be a mine here because if there were, then it would have to extend out here and create a group of 3. So that tells us that this is also not a mine. We can also see, though, in the yellow case, this one can't be a mine because it would have to go downwards, but that breaks the 1. So we can see this one is never a mine. There we are. Okay. So then we can see that in either case, actually, we can just get rid of this. I don't think we need it right now. In either case, we know that this one here must always be a mine, first of all, just because there can't be a group of 3 mines going down. And then in order to finish up the domino, we can just finish up the 3 from that. We know it must go over there. That finishes up this one and also this 4 now. We can kind of see that this one can't be a mine because if it were, then it needs to extend outwards to make a domino, but it creates a group of size 3. So there we are. This 3 needs to be finished, and then we already have a domino here. And lastly, we can finish up this 4 clue, which finishes up the puzzle because we have no mines remaining. So that's kind of how dual logic goes, usually. And we can go ahead and go into a more difficult puzzle. So first of all, by some of the same logic as earlier, we know there can't be a mine there because in order to make a domino, it would overload the 1. The 0 is finished, as is this. This is kind of the same idea as before. There can't be a mine here because for it to create a domino, overloads the 1. So we can then see that this must be the case, just by kind of extending out the domino. We can similarly get rid of both of these. We also know from standard Minesweeper logic that this cannot be a mine. Alright. And now we can kind of consider, for this 1 clue, what happens in either case, because there's 2 possibilities. In the yellow case, we can see that it extends out here, makes a domino like this, and that none of these can be mines. And in the red case, actually, we can also make further claims like that as well. Not sure if that'll be helpful, though, for what I'm trying to show, but will be complete. And for the red case, we can see it cannot go down because that would overload this one right here. So we know it must go over there, and lo and behold, we can see that we have a square that is not ever going to be a mine. So we can just go in and put 1 right there. Then we can actually also see that in either case, this 2 is kind of finished by our single domino going over, and I'll just fill it in to make it more clear, but that tells us that none of these are mines, so we can go ahead and mark them all as such. There we go. Okay. The next thing I'm kind of noticing here is that in the yellow case, this 2 becomes more restricted, with the idea being this one can't be a mine. If it were, then we can see that it can't go up because it would overload this 2, but by going over, it overloads this 2. So this just cannot be a mine. That tells us this 2 must have mines here and here. Can't be a mine there. And we also know there can't be a mine here because this would overload the 2. So this actually kind of just completes at least this version of the puzzle. And we can see that it does work mine count-wise. Now I guess the next thing to do is consider what happens in the red case. First of all, we can see this one still can't be a mine because if it were, then in order for it to go over, it would overload this 2, so we can just mark that. I guess the next thing that we can consider is, I guess just honestly, a good way to think about this now is going to be to consider how many more mines we can really fit in this puzzle, right? So we know there must be 2 mines in this region in the red case, so we can just mark this as such. We also know that there must be exactly 1 mine in this region, right? So then, from this we have 1, 2, 3, 4, 5. We need 3 more. That would put the remaining 3 mines in these squares here. However, that forms a region of size 3 or more, theoretically, so we know the red case can no longer hold. Therefore, we've actually just finished the puzzle. We can just kind of mark all of these, and it's counting all of this as being fine under expert mode logic just because, or rather under expert mode just because it's all logically visible from that argument. So there we go, and I think instead of running through another domino puzzle, or another dual puzzle, the fact that the D works for both of those is a little bit unfortunate. We're just going to go ahead and go into some combinations. I guess we'll start with dual liar, since I don't think we covered liar last time. No, we did not. Okay. So first, well, we know both of these are 1s, and we can kind of use some of the logic talked about earlier to determine this cannot be a mine. And we know that then this 2 also has to be a 1, since, for multiple reasons. One of them is it just only has 2 squares available to it, so it can't be a 3. But we also know that from this 0, there's only at most 1 mine in this region in the first place. Regardless, what this tells us is that neither of these are mines. Now then, one thing we can note here is that if there were a mine up here for the 0 clue, then we can see the domino must extend this way. But we've kind of run into an issue where this 1 clue is already finished, but this 1 clue is not, right? It would need another mine somewhere down here, but we can see that would overload this 1. This all basically just tells us that the mine for the 0 must be up here, which allows us to fill out this. This 1 clue is already finished. It can be at most 2, and it already has 2, so there we go. And we know by some, like, the, I guess, parity ideas we talked about earlier, that there can't be a mine here because that would lead to this 1 clue having an odd number of mines around it. So there we are. We know this clue must be a 1 because there are at most 1 mines around it, or rather 2 mines around it, so that puts us to 1. I guess something we can kind of consider is if the mine's there, then we know this must be the domino because this 1 then needs to be a 2. So we can mark both of those. And this. But then we kind of run into an issue with getting the last mine around this 1. For example, if it's here, then the 1's finished, but we need to still extend it, and that overloads the 0. So then we know it must be here, but we run into the same problem. So this actually tells us that these 1 clues are both empty. There we go, and that this 2 has a 1 right there. Okay, we know from the corner idea with dual that there can't be a mine there. And something else we can kind of consider is this 1 can only go in 2 directions, either down or over. If it goes over, then first of all, we know this 2 is now a 3, so we can just put it there. We can kind of finish up some ideas we talked about earlier. What this also then tells us is that, well, I guess it doesn't tell us a lot necessarily. We know that there can't be a mine here, though, because if there were, then it had to go down and overload the 0. So we know it must be right here, which then tells us that this domino looks like that. We can then kind of fill out a lot of the rest of this puzzle, and this does abide by our general mine count that we have remaining, given that there's 1 more mine in one of these 2 squares. Now, in the alternative idea, we can see that, first of all, we can actually see there are some common unfilled cells here, I guess, for this 0. so we can mark those. We'll also just go ahead real quick and show that we know neither of these can be mines just because this one clue's already finished, so that can't be a mine, and then this one must be a 0. So there we are. Anyway, first we'll go in and put both of these down. Okay. And so we can see that in the yellow case, this 3 only has 1 mine around it, which isn't allowed. In the red case, though, we can still put a mine down there and make a domino like this to finish up the 3. So this tells us that the red case is the correct one. There we are. We can get rid of that now. Okay. We know this 3 must be a 2 just because there aren't 4 cells that could have mines in it around it. Since we already have 1 here, it only needs 1 more in this region. It must be like that, because otherwise it would overload the 3. And this 3 is just finished, it already had 4. This 2 similarly cannot have 3 by the number of open cells, and already has 1 mine around it, so there we go. Same logic applies for this 3, and we see that we have 2 cells left and 2 mines left, so there we are. The next one of these that we're going to go over is dual negation, just because I haven't done one of those yet, and then I'll probably go over maybe one more combination. Maybe not, depending on how long this takes. Let's go in and get into it. So first of all, we can notice that if we put a mine down here, we must then extend it in order to create a domino, and we've kind of run into an issue where we no longer have enough open cells left to really get 2 on this negation clue. Keeping in mind that negation means that the difference in the number of mines between adjacent colored and uncolored cells is what we're kind of looking for here, right? So we can get at most 1, just considering either of those. So that tells us this is not a mine. We also know now that this 2 has 2 possibilities. Either these 2 are mines or these 2 are mines. These 2 are mines, then first of all, we can just do this. But we also know this one must extend upwards like such, and this one must extend outwards like that. There we go. We can also see that in this case, this one here cannot be a mine, because if it were, it has to extend over here, but this 0 will not be possible anymore, because it needs this uncolored cell to finish it off. So we can just go ahead and mark this as a non-mine. In the red case, we can see neither of these are mines because of the 2 clue. In order to finish up dominoes, we must at least extend that one out like that, and this one. This one we don't know, but it's in a corner, so we can deduce that. We can see here this is a common square that is not a mine, so there we are. And now, in the yellow case, we can see that it's either both or neither of these. What that means, though, is if this one were a mine, for instance, we would run into a problem where the 0 is overloaded. So we can see that this one is not a mine. Now, something else we can kind of consider is, for this one, if this one's ever a mine, then we kind of have 2 possibilities around the one. Either this one's a mine or this one's a mine. If this one's a mine, then we're fine. But if this one right here is a mine, then in order to finish up this 0, we would have to put a mine there, which creates a region of size 3. Right? However, something else we can kind of notice, and maybe this is a better way of going about talking about it, is if we put a mine here, then we know this one must be a mine to finish up the 0, but that also tells us that this must be a mine to finish up the 1. So we kind of run into problems there. We can then see that this one is just never a mine, so there we are. Okay. I guess the next thing to kind of consider is that we know regardless of which situation we're in, well now actually we can also see that in the red case, this one can't be a mine because of the same kind of arguments before. It would require a group of size 3, so we can actually just mark that. There we are. Okay. Something we can now kind of think of is we know that this one will have a weight of 0 for both of these clues. We then know that if one of them is up here, for instance, it must then also contain this one in order to get it back to 1 for this clue's size. And this doesn't actually, well, it does matter. This only really applies currently to the yellow case. In the red case, there are other ways we can kind of... No, there actually aren't. Never mind. This actually gives us information about the red case, first of all. We know that if there were a mine here, then this 1 clue would no longer be valid because we can see here it will always have at least 2 more gray cells than black cells, because even if we try to bounce it back out, it just does not work. So we can then mark this one as always being a non-mine. Now we'll go back to my original kind of logic, which is if there's one here, we know that since this will always have a weight of 0, we need this to also have a weight of 0, so there we are. But by the same logic, we can just mark both of these as non-mines. We know that this 0 needs to have 1 over there. We have thus created a region of size 3. So we know this can't be a mine. We then know for this one to have a weight of 0 up here. That also cannot be a mine. And thus that cannot be a mine. There we are. Alright. I guess the next thing to think about is what to kind of do from here, trying to solve this puzzle. So first of all, we know that in the red case, it must go up here like this. What that tells us then is in order to finish up this one, there must be a mine here. Correct? Yes. And that tells us there is not a mine up there. But we also actually know that this red mine can't extend here because then we get this. Same problem as before, so we know this one is not a mine, this one is not a mine. Rather, the way to correctly show this is, since there's only one mine here, this can't be a mine and put it to 0 and there aren't any other squares. This cannot be a mine, this cannot be a mine, and this cannot be a mine just by the 0 clues over here. So this gives us a little bit more information. Like such. There we go. Now we have 1, 2, 3 pairs, so we have 6 mines total. This would then tell us that there must be a group, 2 more groups of 2 here. We can see only one group can kind of fit into this region, so there must be a group here. There we go. That's a common cell between them. Okay. Now, the other kind of thing to consider here is that we know in the yellow case here, and this might be a little bit busy to look at, so just kind of try and focus on the yellow, we can see that this has a weight of 0 for this one clue, so there must be one mine in this group right here. If that mine is here, then for this one to bounce out, we know that there must be a mine there, correct? Because otherwise, we will always have something that is 2 or greater. But that breaks this one, so we know there can't be a mine there, and that the last mine must be there. Just by corner logic, we can see this can't be a mine. There we are. We can go ahead and mark off all of these. However, we now know that for this one, there must be one more mine in one of these two, but if we put it here, we run into the same problems before. So we can then safely say that the mine had to be there. Can't be a mine there. There must be mines in these 2 squares as well. It tells us this one is not a mine. There we are. We can see then in the red case, in order to bounce out this one, there must be a mine down there. In the yellow case, we have already... Well, actually, the yellow case just runs into a contradiction because this must be part of a dual or a domino that we can mark like that. And the yellow case, we have overloaded this one. So this actually tells us now which case we are looking at, and you can see that has been more or less confirmed for us by all of this. There we are. Okay. And this one clue is just going to finish the puzzle for us. We can see it needs another mine to be balanced. We'll put it up there, and then it needs a domino, and we have run out of squares, or rather, we have run out of mines. So, there we are. Okay. Yeah, I think that's actually going to be where I call it for this video. Thank you so much for watching. Next time we will be covering cross, so get excited for that, I guess. Bye.